Video. For chapter 5, we have quite a few like loose ends to kind of look through, some ideas to kind of go over, and I thought making a video would be the best way to kind of give opportunities to go over and also give you time to look at it and see what I did. I've chosen two problems, and I'll use one or both to highlight the one in the middle, the mean value for integral. So the first one is this idea of uSubs, and we talked a little bit about it in class. So I'm going to do an example of a uSub problem, and then we'll find the area between two curves. And then after that, we'll compute the mean value for some interval on these. Okay. So the first one, the uSub. I'm going to integrate this thing. And at first, this integral looks really complicated. First of all, there's a natural log that is inside EV plus one, and then I also see a v plus one in the denominator. So there's a lot of things that are happening here, a lot of different, this integrand is very complicated. Um, but with a little bit of insight and a little bit of practice, you'll start to see things. But one of the things that really stands out to me immediately is then I noticed that there's this v plus one in the numerator and the denominator. Now, something that we haven't explicitly talked about that you will see this unit is that the natural log of, I'll call it, let's go with x, I guess. The natural log of x, if I take the derivative of x, if I take the derivative of this, the derivative of the natural log is 1 over x, and then you have a dx left over, but dx divided by dx is 1. So it's derivative. So whatever I'm taking the argument, whatever the argument of the log is, the derivative is 1 over that. And so I'm really starting to see that maybe the right move to make here for this substitution is to let v plus 1, log of v plus 1 equal the u. And then the derivative of that will actually help cancel out. That'll be part of the du piece because there's going to be this leftover term over here. Let me just finish this off. So if I'm doing it implicitly, then the derivative of natural log of x is 1 over x dx. Okay. So this kind of has that same form where the x here would be this v plus 1. And so that would be really nice because that helps us to utilize the property. Now you might be thinking, well, what about if I take the natural log and I have the square? Can't I use that property of logs to bring that down? And that's true if the argument of the log has the square, but this is actually on the outside of the natural log function. So I can't pull down that square down in front as a 2 in front since it's acting on the outside of the function. So taking the log and then squaring it, taking the argument of something squared. Okay, not taking the log of something squared. Okay, so this is the thinking that kind of goes into a careful substitution for it. So we're going to let we'll call it u equal the natural log. So it's going to be the whole thing inside the square. Because again, we're going to take the derivative and you'll see that this v plus 1 downstairs is going to cancel out. V plus 1. This is a v. Okay. So I'm letting u equal this quantity. Okay, which means then if I implicitly differentiate, du is going to equal the derivative of natural log, as we saw, is 1 over whatever I'm taking the log of, v plus 1, times the derivative of the inside, which is dv. Okay. So now if we're comparing, something really nice happens here. Do you see that everything that I've highlighted is exactly the du piece? So I can actually kind of like brush all of this aside, and that just gets replaced by du. Okay. Likewise, since I've substituted in u for the natural log, this just becomes u squared. And the last thing I can do is plug in the values to figure out what is this equal to under the new substitution. So u of 1 is going to equal the natural log of 1 plus 1, which is the natural log of 2. So that will be my lower bound of integration. And my u of 3 is going to equal the natural log of 2, no, sorry, 3 plus 1, which is equal to the natural log of 4. Okay, so that's my lower, or my upper, my upper bound and my lower bound. Okay, so I'm going to rewrite this integral now with all the information plugged in. So the upper and lower bounds are natural log of 2 and natural log of 4. I'm replacing the natural log of b plus 1 with u, so it's going to become a u squared. And then the highlighted part, the dv over b plus 1, is this going to be my du, okay? And so now using the power rule, all I need to do is take my add 1 to the exponent and then divide by it. So I'm going to have 2 plus 1, which is 3, u cubed, evaluated from my two limits of integration, natural log of 2 and then natural log of 4. Okay, so I have 1/3, using fundamental theorem of calculus, the natural log of 4 cubed minus the natural log of 2 cubed. Okay. There is quite a bit of simplification that we could do with this problem, but for now, we'll just leave it in this form. Okay, so this integral, while at first it looked really nasty, with a clever substitution, identifying that the natural log of x has the derivative form of 1 over x dx, that allowed us to be clever with our substitution, and then you'll see that with a good substitution, right, your integram becomes much simpler than the previous version. That's how you know you have a good substitution. Okay. All right. So I hope that that was helpful. Now let's look at this next problem, which is the area between these two curves. So we're going to look at the area between the curves. I should really call it like that, y1 of x, but anyways, y equals x squared, and the second one is y equals 4x minus x squared. Okay. So getting a graph of these two, getting a picture, I always find is very, very helpful. Normally we would just graph it, but with modern technology, we do have some options that allows us to be a little bit more what's the word? A little bit clever? Is that a word? A little bit more mindful. I think it's something like that. So, so we're going to go ahead and use some technology here. I'm just trying to get the right screen size so we can actually see what we're doing. There we go. Okay, so here I am in GeoGebra. All right, and okay, so I think we're good. So we're gonna have x squared. There's the first one, and then the second one is 4x minus x squared. Okay. So, so you can see the overlap. So we're looking for this bounded region right here. That's what we're looking for. Okay, so we have to figure out, it looks like these are going to be pretty easy to find where the points of intersection are. Okay, but just to do it algebraically, and in cases when you know, maybe it's not so easy or not so obvious, it's good to have that connection. Okay, so so the way that you find it in general is just to set, you know, that when you're looking at the graph of these two things, the y values will be the same. Okay, and so we set these two equal to each other, and so you get x squared is equal to 4x minus x squared. Okay, so you can either add over or subtract over, whichever you need to do. The x's are opposite sides, so they're not going to cancel out. So I'm just going to probably add and subtract to the 4x and the x squared. So I get 2x squared minus 4x is equal to 0. There's a common factor of 2x I can factor out, so 2x. That leaves an x minus 2 on the inside equals 0. So the zero product property says that either x is equal to 0 or x has to equal 2. Okay, so those are the two values then that we saw as the limits of integration. Okay, and so the next thing to pay attention to is the order, like which function is technically higher, you know, has a higher y value, like we saw on the other example. And so if we look at this, coming back to this one, you see that the red graph here, which is the graph of 4x minus x squared, is actually the function that's on top, if you will, on this interval from 0 to 2. So it's going to be the area of this one minus the area of the green one here. Okay. And so that difference then will give us the area bounded between those two curves. Yeah. So so if we're kind of, if I'm going to kind of sketch the area of interest here, this is kind of the graph that we're looking at between the areas of interest here. So this top function here, this is the 4x minus x squared. Okay, and then the bottom one here is the y equals x squared. Okay, so the radius, if you will, of the height of the rectangle that we're looking at are really the ones. This is the one that's giving it the area, and we're going to subtract off of it this area here. Okay, because the area that we're interested in is this region in here. Okay, so we found that this has the ordered pairs of 0, 0, and 2, comma, what before, I guess. Okay, and so these are the x values that we're going to be integrating over. Okay, all right. So calculate the area in this shaded region. Then the area, the bounded area, is going to equal the integral from 0 to 2, the upper function. So the height of that one is 4x minus x squared minus the height of the lower region, which is x squared dx. Okay. So all I need to do now is integrate this. I can do a little bit of work, noticing that I have a minus and a minus. That makes this a, I don't know if it's an easier integral. It just maybe reduces the number of integrals I have to do. That's going to be 4x minus 2x squared dx. Okay. And now I'm just going to use the power rule on both of these using the linear operator properties of integrals. I can write this as the difference of two integrals, but I'll just do that here. So this is going to be adding 1 to the x1. There's like a 1 on this one. So adding 1 plus 1, that gives me 2. And I'm dividing by it. So it's going to be 4 divided by 2x squared, evaluated from 0 to 2, minus, I have a 2 here. I already have a 2 on the x on this. So I'm going to add 1 to it. So it makes it a 3. And then I'm going to have an x cubed up here. And I'm going to evaluate that one also from 0 to 2. Okay, it looks like I'm running out of room. Here, you should note that you have 4 divided by 2. So those are going to cancel, leaving us with 2. Okay. And how you plug in to simplify is really a matter of choice, of personal preference. I'm just going to plug it in individually here, but normally I would factor something out and plug it in, do it a little bit differently, but we'll just go ahead and plug it in. So I have 2, this 2 right here, times, I'm doing the upper limit, 2 squared minus 0 squared. So that's this one, minus 2/3. That's this one, 2 cubed minus 0 cubed. Okay. So obviously the zeros don't matter. This is 4, and then 4 times 2 is 8. I'm subtracting from 8. This is 8 already, and then I'm subtracting from that. Not subtracting from that, I'm multiplying it by 2. So 8 times 2 is 16. This is 16 over 3. Multiplying 2 times 8 is 16 over 3. Okay, so getting a common denominator, I need to put this over 3 over 3. So this is 24 over 3 minus 16 over 3. 24 minus 16, of course, is 8 over 3. And so the area bounded by those two curves is 8/3. Okay. All right. So now that we have both of those done, so we've shown how to do a uSub. This second integral, the area bounded between the two curves. Notice we didn't have to use the uSub. We just used the power rule here. We also used the power rule on this one once we had the uSub. Okay, so we did the uSub. There was an example of finding areas between two curves. And so what about this mean value? What is the mean value? Okay. Now let's dive into the mean value. So in lieu of the more complicated problems, I thought it would be beneficial to kind of focus on a simpler problem. So we're going to look at the integral and find the mean value of this function y equals x on the interval from 0 to 8. Okay, so geometrically speaking, this shouldn't be too surprising. 1, 2, 3, 4, 5, 6, 8. Okay, so here is a kind of a rough sketch of our function. If I was a better drawer, that should be right through each of those. Okay, and so we're looking at say the right 1, 2, 3, 4, 5, 6, 7, 8. Okay, so we're looking at this region right here. Okay, so here is where x equals 8 and x is 0 here. So we're looking at this region here. It's in the x value. Okay, and then we're looking at well, in this case, the height here is also y equals 8, since that is in fact. So it's really this region that we're interested in. Okay, and so what are we trying to do? What are we trying to figure out here? Well, the mean value is the average value. So let's compute it and then kind of see if we can make sense of it geometrically with this particular problem. Okay. All right. So the mean value says that it's 1 over b minus a, the integral from a to b of f of x dx. Okay, so that's the formulation of it in the theorem for the integrals. Okay, so that's the mean value. Okay, so let's plug it in. Our interval is going to be 8 and 0, so 1 over 8 minus 0, the integral from 0 to 8 of x dx. Okay. Well, the integral using the power rule is add 1 and divide by the exponent, so it's 1 plus 1. So this is 1 8 times 1 over 2 x squared, evaluated from 0 to 8. And I'm going to leave it in this format since we have some symmetry things that are happening out. And also notice that the bottom limit is 0, so that will be canceled out. So I'm just going to worry about plugging in the top value. So this is 1 8 times 2 times 8 squared minus 0 squared, just for completeness sake. But like I said, that one's 0. Okay, now notice I have 8 squared here and an 8 down here, so one of those 8s is going to cancel out. So I have just an 8 left over upstairs, and then I'm going to divide that 8 by 2, and so that gives me a total value of that. Okay, so the average value is equal to 4. Okay, so remember that our f here was y equals x. So what this is really saying is that y is equal to x. Okay, so if I wanted to know the if there was a f of c that made this true, because y equals x, it's actually x equals 4 is the same value. Okay, so what does this mean geometrically? Well, y is equal to 4. So if we come up here, 1, 2, 3, 4, and I draw a line here at y equals 4, what this is saying is that the region that is the area under this curve, this region that's highlighted here in yellow, that bounded area is equal to the corresponding rectangle at this height of x equals, or y equals 4. And the x value that provides that happens to be, of course, the same x or y value, because it's y of x. That's not usually the case. It's just a coincidence when you have the identity function. Okay, but the fact that we have this rectangle whose height is 4 and base is 8, that gives us an area of 32. Okay, so 8 times 4, that equals the area of this rectangle. That area is equal to the area of the triangle that's formed here, this 1/2 base times height. Well, the 1/2, the base is 8, that's the same base, but the height here goes all the way up to 8. So half of 8, well, that's 4. Oh, look, it's the same thing as 32. And so what is the mean value? The mean value is it's a y value that says that the area of the entire shape. Now, this is some nice geometry, so we can kind of see the geometric relationship. And so for more complicated curves like this, right? The average value is still some y value, such that if the region totally under the curve, this is a bad example here, but you can kind of get the idea that the area, maybe the function goes over here like this, right? And maybe it goes down here. So this is the region here that we're looking at. Okay, so here's the region of f of x. This whole region, that bounded area is equal to some value of f of c is equal to y times it's the same, the length here, drawing it like you can see it. So in general, it's saying that, look, this distance, b minus a, okay, that's the base of the rectangle, times the height, which is f of c, okay, this is equal to the f average of the function. So this other rectangle, okay, is the same area or equivalent area as the area of the bounded function. And that's what we found here with a similar geometry. Okay? So we have a triangle, and the total region or total area bounded in this triangle is equal to the area of this rectangle with a height of 4. Okay, so what is the mean value theorem really talking about? It's saying you give me a function that's continuous on the closed interval, right? So it happens to be that the function f has to be continuous on this interval and differentiable on this interval. Okay, so it has to be f is continuous on this interval and differentiable on this interval. And if that's true, okay, then I can give you a value, a y value. Okay, it's actually a c value in, so there's some value of c in AB. Okay, that when you evaluate f of c, it's equal to the average value of that function, which is this height here, which gives you then the corresponding rectangle that captures the same area as the total region. So I just think that's really cool, and it's an important feature to be able to know. Okay. All right. Well, I hope that was helpful, and I'll see you in the next video.